Thanks everyone for joining us tonight. I'm Bunny Tucker. I'm co-chair of AIA Philly COAT, along with David Hincher, fellow co-chair. We're joined by a number of members from our 2030 subcommittee. We've got an exciting new series of sessions coming up over the next half of the year. We kicked it off last month with the new DDX, an introduction to that, and some research on data viz. And tonight we're going to be shifting into looking at energy models and playing a simulation game to understand what goes into it and why it matters. In March, we'll continue with a focus on energy modeling. And then in April, we're going to sort of shift gears to bioclimatic design, followed by a session on thermal comfort in May, and then 2 sessions on sunlight and daylighting during sunny summer hours. Then we'll move into embodied carbon and then wrap up this whole series on breaking down barriers to building science in September, looking at what all these numbers mean, how best to report your data, and sort of tying it back into the DDX and reporting it and best practices for that. So thank you all for joining us tonight. We're really excited to see so many people in attendance. If you haven't already, please include your name and email and AIA number for credit. And I'm also really excited to introduce our new co-chairs for the 2030 subcommittee this year, who are going to be kicking off this session. We've got Janki A, who is an adjunct professor or adjunct faculty at Thomas Jefferson University and a former colleague at Kieran Timberlake. She has extensive experience with energy modeling, and we're just so excited to have her on board. And we also have Josh Abbell, who's been part of this subcommittee since its inception. And he is an associate at Ballinger and leads up a lot of their 2030 reporting and sustainability initiatives internally. And we're excited to co-host this series of sessions with AIA COAT New York. We have Apoorv Goyal joining us from Elementa Engineering, and he's also going to be helping steer this session in combination with Kieran Kennedy and Aishwarya Katta. Did I get that right?
Yes, you did. You're good.
Thank you, from Jacobs and Digsall. Thank you all to thank you so much to our presenters. And I'm going to turn it over to Janki. Don't forget to sign in, include your name and email address and AIA number.
Hey guys, I'm Janki, and Josh is actually going to start the presentation, and I'm going to kind of just navigate for him here. So go ahead, Josh.
Okay, are you in control of the screen, Janki?
I am. Would you like control?
All right, sounds good.
Okay.
So welcome all. As Bunny suggested, we got a lot of positive feedback to our talks on energy modeling last year. And also we had a lot of attendees, and also as we did some end of year surveys, we heard that there was still a lot of interest in hearing more about energy modeling. So out of the gate this year, we decided to set up 2 talks on energy modeling. And this one is going to kind of focus on the earlier uses of energy modeling. Next month's talk will get a little bit more into to whole building simulation. We'll talk about these terms, but we wanted to just kind of go through some of the basics and we kind of talk about some of the kind of review the fundamentals of energy modeling, but also talk about some of the ways that energy modeling is evolving in our practice and ways that we can really use it in our design process, and also not just the ways we're kind of accustomed to it historically, more on the engineering side, but how as architects we can engage in energy modeling. So we're going to do a quick talk at the beginning here, kind of laying out some of that groundwork, and then we're going to move into a simulation game, kind of an exercise, that kind of explores how to do that very task of using energy modeling in an iterative way at the beginning of a design process. And then once we come out of that, we'll split into 4 breakout rooms. We have a lot of people on the line today, and we'll kind of reflect and talk about some of the findings from our models, and we'll have some time for Q&A and closing up our talk. Go to the next. Oh, and I should not forget, for those who are still joining, to please enter your AIA number, name, and email as you see on the right. Just enter it into the chat, and it'll be recorded. All right. So what is a building energy model? That's our first question.
Did you already give mine?
Your camera's on.
And I guess if I could ask people to mute too as well. So what is a building energy model?
Spend a bunch of time worrying about that.
Why don't we go on to the next one? So here, Janki, can you go to the next one? Thanks. So, I mean, at its heart, a building energy model is a mathematical simulation of, what's supposed to be real world conditions. They are just that, though. They are simulations, so they are inherently affected by the input. The output is inherently affected by what's put into them. So the thing I think we want to talk about today is how we use this mathematical model, this simulation, as a tool in the design process. And it's also important to understand, what types of energy models we can, expect to perform as architects, as engineers in our process. So I think many of us are pretty familiar with the whole building simulation, the end of the project, the end of the kind of CD, DD phase, building simulation calculation. You might use it for lead or use it for code, but there's a lot more that you can use energy models for. And among those things are the single aspect simulations. So this is looking at specific elements, specific variables, and looking at the impact they have on design. And this can happen throughout the phases of the project, but it's an important piece, aside from the whole building simulation. So, and then we'll talk about how to use, and through the exercise we're going to do, we're going to talk about how to use energy models to help make design decisions and optimize our projects. Go ahead. Next slide. Okay. So what can you learn from an energy model? Let's go on to the next one. So there's a lot of guidance out there for energy modeling, and it's important to kind of settle on some of these terms and understand what these things mean. The book you see I guess pamphlet you see up in the upper left is the Architect's Guide to Building Performance. This is actually put out by the AIA, so it's literally a guide for architects to help make use of the energy modeling process in our process. And so, as I mentioned, single aspect simulations can be looking at variables like massing, shading, daylight, envelope, R value, thermal comfort, and ventilation. And then whole building simulations, not just the end of project or late phase simulations that we were talking about, but whole building simulations can really be brought up to the earliest phases of conceptual design. And actually, as we'll talk about, they can be done before you even have put pen to paper as far as design goes. I know we don't use pens and paper anymore that much, but you can use them just to establish what the most important variables are going to be energy-wise. You can go ahead to the next slide. Okay. So this comes out of the Architect's Guide to Building Performance, but this lays out the actual ASHRAE 209 energy modeling standard cycles. And I think it's useful, and then it just kind of helps identify some of the discrete uses that you can find for energy models, how you can employ them early in projects. And I think the most important thing, I think as I've started to mention, is to learn how to use energy modeling as an iterative tool, to understand what questions we can ask, what decisions we can make, what modifications can we make that will set us on our best course forward. And of course, this is a 2030 commitment talk and subcommittee presentation. So one of the first things to do is actually set your target. And this is an underrated piece of the process, to set your goals. And we highly suggest using the AIA 2030 DDX as a tool for setting that benchmark, setting that baseline and setting your target. Understanding what other projects of similar size in similar climate zones can do. And there's some other Energy Target Finder, the laboratory benchmarking tool for labs. These are all useful methods for helping set targets even before you really know what your project looks like and how it's going to develop. So one of the first steps, and this will kind of be explored in our exercise, our breakout exercise, is the simple box model. So this is before we've even started to establish design concepts, to understand what a simple box building would look like in our site, in our climate zone, and what variables would drive the inherent loads on this building. And this is without considering mechanical systems. This is before we've brought an engineer in. Again, these early phases are really opportunities for the architect, for the designer, to kind of try out some of these options and understand what kind of loads we're setting up for our mechanical engineers to address. So, and then the second cycle, the conceptual design cycle, you started to develop building geometries. You started to develop a few schemes, maybe just in massing, very simply, maybe. But you can start to understand what variables, what trade-offs you're seeing between the different concepts. And then load reduction. This is kind of as you're getting towards the end of schematic. It can be pretty useful to have an engineer engaged at this point. Start to talk about anticipated equipment loads and things like that. But really, those first two cycles, could be done almost exclusively by an architect with the right tools. But as you'll see, some of these tools aren't very complicated, and a lot of these principles are fairly fundamental. And so, I think there's some previous talks that we'll refer to at the end that we can talk about. So this next slide is about the energy modeling at later phases. Again, these are the more familiar advanced simulations, bringing in cost, more realistically. How do we optimize mechanical systems? How do we compare mechanical systems? And then the other thing to mention too, though, is even at these later phases, you can kind of pull out, do a single aspect simulation, do an envelope analysis, do a facade analysis, do a shading analysis, and kind of look at how those more finite studies can impact continue to impact your project. You can go to the next slide. So when should you run an energy model? And I think I've already started to kind of talk this through, but this is the diagram. This is one of the diagrams. There's a million of these diagrams out here about when to do different phases of energy modeling. As you can see, they're a little bit blurry, but this diagram, may be a little bit too linear for some. So, but it shows that you can kind of continue to kind of look at these things into the design development phase, for example. Whereas the simple box model, you want to leave, and the conceptual design models, you certainly leave those behind in the schematic and preliminary design phases. Okay, next one. So Janki and I were talking about different diagrams. The last diagram really tell the whole story. And I think the thing we wanted to make the point of with this diagram is that design is inherently an iterative process. So there's a multitude of issues that we're thinking about throughout all of these phases. And this kind of shows, I think a lot of the considerations that are all being kind of considered at the same time, considered holistically, that kind of cause us to kind of spin our wheels a little bit in the beginning of a project, to go run through iterations, figure things out. So I think we just wanted to highlight that this is not such a linear and clean process, as I probably don't need to explain to most of you. Go ahead. Yeah. So this diagram actually shows kind of the more traditional method of using energy models in the design process. And it really shows the architect, what it's meant to illustrate is, the architect developing their design, sending out their design for some feedback, which they may or may not get in time to actually do something with. So again, just kind of emphasizing the importance of the architect being able to kind of, try out some of these variables and get quick feedback, instant feedback on how these variables can affect, the ultimate loads, the ultimate performance of their project. And so this next diagram that you're looking at, is kind of suggesting how to kind of break down that traditional process and actually having some time to react to the feedback and move forward with the design. Okay, next slide. So what does it cost to run an energy model? And I would say I'd like to steal a quote from Kim Shin, who gave a great talk for our group last summer. I think it was last July, and there's a video of this on the COAT Vimeo page. Basically, his phrase was that it was pocket change in terms of the design costs, in terms of the mechanical design costs, for example. And Brian's actually provided us this study that shows that for this group of, I think these are HOK and TLC projects, really any project over 25,000 square feet, a full-blown performance simulation paid back in generally less than 6 months, not just within a year, and oftentimes within 2 or 3 months. So it really is a small piece of the big picture, especially when you consider the payback that these decisions can generate long term. Next slide. So with that, I'm going to turn it over to Janki, because when we get into tools, we get a little bit out of my element. So we're gonna go through the tools with Janki.
So I think I'm going to try my best to demystify tools, or at least go in depth on them. We did have a session last August, which was our most widely attended session on tools. But there's a lot to unpack there. And so I'm going to try to kind of take a stab at that. I consider all of the tools to be a kit of parts. There's no one tool that can do everything. There's 3 main categories that you should be familiar with regards to the tools. The first and the most important would be the simulation engine. So if there's any engineers on the line or on the webcast today, you're probably familiar with DOE 2, and you're probably using it for the in-depth engineering type analysis. You're also probably familiar with Energy Plus. These are the 2 main engines that are used for energy modeling. There might be some other ones as well, but these are the 2 main ones. And before we go into the rest of the kit of parts, I think it's important to understand the history of energy modeling so that we can put into context why energy modeling is or seems to be inaccurate. Energy modeling started in the 70s, and it started with the US Post Office of all places. They wanted to understand their energy use, and so that's where it started. And this is before the DOE was actually developed or created. And before, right after the post office program, there was Cal IRDA, which eventually became what we know as today the modern Department of Energy. But it took about 20 years of development. And so the Cal IRDA program was renamed DOE-1, and for nearly 15 to 20 years, that was the program that was used. In the 90s, J.J. Hirsch and Associates secured the rights to DOE-2 and started developing DOE 2.2, which is what we use with EQuest today. But when the rights to DOE 2.2 were given up, the DOE actually rebooted a Department of Defense program called BLAST. Of course, the Department of Defense is going to have a program named BLAST, but it was renamed to Energy Plus, and the first release of Energy Plus happened almost a decade later. And once Energy Plus was released, this is like a period I call a period of transition. So there was about 20 years of transition where there's trade-offs, departments were changing, and the change that we're seeing with energy modeling today, or the emphasis or the accessibility of energy modeling today, really happened when Energy Plus was released with Open Studio as an open source license. And shortly after it was released as an open source license, Autodesk actually took that software and converted it to C++, and as part of a program with the DOE, and then re-released it as open source. So all of the growth that we're seeing in the tools that you see today actually has happened in the last 6 to 7 years, and it's just beginning. So when something is just beginning, it's the right time, in my opinion, to get on board and like really fully embrace it. So that's like a little bit of a background. Oh, sorry, one more thing to mention about that is for nearly 40 years, the primary use of energy modeling, even though it started off to analyze energy use in post offices, was to design systems. And now that we have interfaces that allow us to interact with the energy modeling tools, we're starting to use it to create better designs. So the second part of the kit of parts is your actual 2D or 3D modeler. The three most common that we use right now is SketchUp, Autodesk, Revit, or Rhino with Grasshopper. And then we have what we call a user interface. The user interface is what we're most familiar with, right? We have Open Studio, Cove Tool, Honeybee. Solema has Planet Studio, which was released last February, Sapphira, Autodesk Insight 360, IES. I believe with the exception of IES, every single one of these user interfaces uses either Energy Plus or DOE, or a combination of the two to run the energy model in the back of the house. So here's an example of what would all of the tools or engines or modeling softwares that are used in order to run an energy model. So this is just one example. If you're modeling your geometry in Rhino, you can use Grasshopper, or you can use just Rhino and connect it to Honeybee, which is a plugin for Grasshopper, which uses the simulation engine Energy Plus through Open Studio. So it's complicated, but once you understand the lay of the land, I think it's easier to start asking the right questions with regards to how you should be modeling to get an accurate model, like accurate results in your energy model, right? The makeup of the kit of parts will inform the accuracy of your energy model, okay? And I'm gonna kind of end the tools talk on, do not feel like don't become the victim of your tools. Don't be left behind. This is just beginning. If you saw the history, we've only been developing these interfaces for the last 6 to 7 years. there's going to be a lot more that probably will come, and we just need to kind of own it, embrace it, and really make it a part of our design process, really integrate it, right? So let's dive into some of the factors that can affect the accuracy of your model, right? Most people have probably heard this before, right? Garbage in, garbage out. What you put in is whatever quality you put in is the quality you're going to see on the back end. With regards to energy modeling, the two biggest sources of error that I've seen in my experience has been human judgment, right? There's the human aspect with regards to the inputs, and then the interpretation of those results is just as important. And there's inconsistencies, right? Different modelers will use different experiences to inform how they do design. Now, when you use an automated energy modeling process, and what I mean by that is a user interface that automates the energy model and gives you quick results, they're making those assumptions for you. And so if you're going to rely on it, you have to understand what those assumptions are before you can say, yes, this is accurate for my particular instance or not. And then the second thing I would say is more related to geometry and how it is created in your 2D or 3D modeler. Any automated process right now, if anyone's been using, I don't want to call out any softwares, but if you've been using any of the user interfaces out there to energy model and you're seeing errors or the numbers don't make sense, I guarantee you it has to do with your geometry. Anything that's automated, you have to go in there and double check it. Each engine has a very specific requirement for how that geometry needs to be modeled. And because an energy model requires a very simple geometry, it also requires accuracy, right? There's no, 2-inch tolerance or gap here or gap there that you might have when you're doing a rendering. You have to be precise and you have to be simple. And you have to abstract the geometry that your architectural design model might have in order to speak the language that the engine needs, right? So, and anyone who's doing energy modeling or daylight modeling, I guarantee you right now, you're not taking a BIM model and trying to clean it up. You're probably just going to create a new simple model with your ortho snaps on, make sure everything's tight and precise in order to be able to run your energy model. So this is one of the topics that we're going to unpack further in March. We want to understand what geometry mistakes are we making? What are some common modeling errors? So I hope you'll join us in March to learn more and see examples that can help you with your energy modeling journey. So when you think about garbage in, garbage out, I guess one of the questions that comes to my mind is, shouldn't there be a standard to minimize factors that reduce the accuracy of an energy model? Well, there is. There's the ASHRAE standard 140. So this is a standard that regulates the engines, right? And the biggest source of error here, or not even a source of error, it's really a factor of resolution. All of the testing and validation of the engine happens against other engines. So that validation isn't happening against the real world, right? We don't have enough real world data to inform these engines. And so it's kind of like just testing against each other. And that's why we need to start reporting our data and using the DDX or other reporting tools. It will help build up our energy modeling capabilities in the future, right? So right now, I would say the primary target audience for ASHRAE Standard 140 is Energy Plus. IES has an Apache system, I guess, and then there's a couple of other engines out there that are to the ASHRAE Standard 140. And then there's also a new standard under development right now. This is ASHRAE Standard 229P. This standard is trying to address the issue with user interfaces, abstracting or automating energy modeling processes for people like us, like architects, who may not know everything that you need in order to meet like the engineering requirements for energy modeling. So in ASHRAE standard 229, one of the biggest things that they're going to try to standardize is a rule set. And to put this in context of language that you might already be familiar with is the energy cost plus budget method, or the performance rating method in ASHRAE 90.1. Those are rule sets, right? It's very clearly, well, loosely clearly written out rule sets that are tedious to implement manually, right? It seems like something that you can totally automate, but there needs to be standards for that automation. And that's what standard 229P is hoping to do. And it will probably be out in the 2022 code cycle. So anyone who's complaining that this user interface doesn't give me the same result as this other user interface, I think the standard is going to address that to a certain degree. Okay. And then another aspect that can result in errors with your energy model is weather inputs. The question that comes to mind is where, how, and when is weather data collected? We have something called TMY3 files, and if you read the full name, a typical meteorological year, it in itself can help you understand why that might be a source of error. And it's also using typical meteorological data from 1991 to 2005. And the way this file is compiled, it's compiled in what's called an energy plus weather format, the EPW. It takes the most typical or average or median condition of every month, hour, and day from that 20-25 year span to aggregate a typical year. Now, if the last 5 winters are any indication of climate change, there's no typical meteorological year anymore. So we want to be able to model for future occurrences and not necessarily just historical data. And weather data is also recorded at an airport at a height of about 30 meters. Now, if you're working on a residential building and you're taking wind data or weather data from an airport location, you have to kind of downsample it to the size of your building, right? You're not, unless you're doing a 3-4 story building, the data that's recorded at that height might not be relevant to the height that you're designing to. And then some of the data is manually entered at an airport. Some of it is automatically recorded by a weather station, and some of it comes from satellites in space. I've spent the last 4 years trying to figure out exactly how all of this data comes and from which data, like which government agency. I haven't quite figured that out yet, but hopefully soon. But so that's a source of error. And then even if we're to project out for future climate, there's a weather in weather. We can barely get weather forecasts for the week to hit the spot. Like it just says it's gonna snow, maybe it doesn't snow. So we do energy models for a whole year, predicting data based on past data. It's just something to keep in mind when you're using these files. And then the next topic would be to be aware of the default values. So all of the assumptions and default values built into an energy model is based off of residential energy consumption and commercial building energy surveys. Oh, I missed a C over there. And these reports come out every few years. And so this data is, if we have grown our digital capabilities so much in the last 6 years, these data sets just can't keep up, and neither can the performance data that HVAC systems, the more efficient systems that are coming out, it just can't keep up with updating all of the default values for the newer equipment coming out, right? So these are things that you would have to go in and manually change if you want a really accurate model, right? If you know the systems that you're using, you can update that manually, but otherwise you're relying on default values which might be outdated, right? And then the other aspect is the human factor. Predicting building use is really challenging. So these are two charts from a NREL white paper looking at an educated user with good behavior versus a typical user of a computer. And when someone's actually going in there and saying, Monday morning I came in, I'm going to turn my computer on and I'm going to put the energy savings on my monitor and make sure my monitor goes to sleep when I'm not at my desk, that's good behavior. But someone who's just leaving their machine on, so those are things you can't predict, right? We know this. It's hard to predict if you're going to have all good users or all typical users, right? So there's this famous quote that probably I'm hoping everyone's heard: all models are wrong. And it was the influence of the title, right? But some are useful, right? There are thousands and thousands of inputs for small buildings, and larger buildings can have hundreds of thousands. So when we use single aspect or shoebox models that were discussed earlier in the presentation, it allows us to minimize our inputs and learn about energy trade-offs. And this is what we're going to be doing in our exercise. And I want to, in the next session. And then we're not the only profession that is dealing with models and accuracy of models. This actually, this article about employment was part of my New York Times newsletter this morning. And so I thought I should just totally add this. Economics, they're predicting models all the time, right? And there's people involved there, and they're making a judgment in terms of their inputs. And so the questions I would ask myself is, how often do we paint a rosy picture of building use as it relates to energy, right? Should our models be idealistic or realistic? And if they're realistic, and the results show increased energy use, how can we use design to inform good behavior? So that's going to be one of the things that we're going to talk about in May when we talk about thermal comfort and how we can use thermal comfort modeling to make design changes to then inform our behavior within a space and ultimately inform energy efficiency. Yep. And then also, because we're currently in a pandemic, this is an article that I had come across at the beginning of the pandemic, where even with the epidemiological models, the New England Journal had to publish an article that talks about questions, right? You have to question your model in order to understand it and for it to be useful. Otherwise, it's just information for the sake of information. And so I won't go into all of this for the sake, but we are going to share the slides, and this presentation will be shared with you guys live. And with that, I think we are moving into the energy simulation game. Apoorv, do
Yes.
you want to?
Hey,
All right.
yeah, thank you. That was a lot of good information, I hope, about the process and the energy models and everything. And what we have planned today is basically to kind of take all of this information that you just heard in the last 40 minutes and do a quick little 30-minute activity. It's not a teaching exercise. It's supposed to be a very interactive exercise just to understand how the energy model works, and look at some of the inputs and what are some of the outputs, how to decipher them. So what we'll do is basically divide ourselves into 4 groups, and then play a little game. It's an energy simulation game that it was kind of started in Harvard GSD, developed further at MIT by Rhino. I've played multiple versions of this game back at GSD and in my professional life. The idea again is basically to look at how can you go to the next thing? Look at how different design variables, which are listed here. It's of course not a comprehensive list, but the main main design variables that we, as architects, as designers, we come across, or as engineers, we come across very, very frequently. There's a cost attached to it, so that the idea is basically, of course, we cannot all have everything. There's always going to be a cost component attached to it. Try and minimize the cost, or try to stay as low cost as possible, but achieve higher efficiency, energy efficiency. If you go to the next slide, and we'll talk about these in the focus groups further. So what we'll do is basically we'll use Rhino, Grasshopper, and Climate Studio. Again, Climate Studio is a tool developed by Solema, by Christoph Reinhardt, John, Timur, the whole good team. I think a lot of you might know them. It's a simple energy modeling script, and you can see there are a bunch of settings, that goes through the facade areas, that goes through some envelope settings and some system settings. There are cost premiums attached to it, and then each time we change anything, we'll run an iteration and try and understand what and how that specific setting impacts the energy use. Go to the next slide. And the idea is basically to run multiple iterations, so that we can continue to track how each of these iterations or these studies impact the energy use. Go to the next one. Look at operational carbon. Next one. I think very importantly, also understand on a monthly basis or versus an annual basis, how does the energy use, and what are the different components of the energy use when the engineers or when your consultants talk about EUI, what do they really mean? How is that broken down, and what can such charts like these help us understand in terms of optimizing the architecture design and having a informed conversation with the consultants. And the next slide, which is even more important as a chart, which is just looking at the energy balance. So instead of talking about energy, talking about loads, again, we can have a more detailed discussions in the focus groups.
There you go. I think we're ready for the breakout groups.
And I'm ready too. I've got it all queued up.
Awesome.
Excellent.
All right, so just a reminder to our 2030 liaisons, Brian, Josh, Bunny, and Jonathan, make sure that you're recording your session. So down next to share screen is a little start recording. So if you record, then we'll capture all of the breakout room sessions. So we're going to set this to 30 minutes. You'll get a automatic reminder about 2 minutes towards the end that it's about to close up, and then it'll push us all back into the main space again. So with that, here we go down the rabbit hole.
Hey, I don't know if I got put in a room. I joined really late.
All right, let me yep, you're not assigned to a room, so I'll assign you to one now. Thanks for joining us, Josh.
Yeah.
All right, you should have a little pop-up there. Oh, Brian, what happened?
No, I came back. It wouldn't let me record. It said the host had to give me permission.
Oh, crap.
So I don't know what has to happen there.
Okay, but you're going to be in first session. Okay.
Yeah, I'm going to go back in now. All right.
All
and
right.
Real quick, we're taking screenshots of EUI, and what was the other one? Monthly? Monthly
I think
EUI?
it's that last slide in the game where it has the EUI and the cost.
Right. Okay, cost. Right. Gotcha. All right.
All right, so you're in room 1. God damn it.
in the chat box, and I believe everyone in the group should have gotten it. Let me know if you didn't. It basically has it's a PDF with each of the parameters that you would change. And so the
building in New York, and basically manipulate variables and look at the impact of those variables on.
Sorry to interrupt you, Josh.
Yes.
I had to come in and allow you to record, so you should have that ability now. All right.
Thank you so
I'm
much.
just going to hop into all the rooms.
All right, I wasn't allowed to record, so
Yeah, you got permission now.
thank you.
No problem.
First is we're getting, sorry, my screen is lagging a little bit. We're getting the area, we're getting the cost that we're kind of talking about, and that will be representative of some of the choices we're making.
Kieran, sorry to interrupt. Bunny, I just gave you permission to record. I got to jump into all the rooms to do that. So I'm going to hop out and go to room 4. Sorry, keep going.
Yep, and so then we're getting EUI down here.
With the variables that we have, we're going to start running some results and taking screenshots of the EUI and the carbon emissions. And our basic idea is to make sure that we have a very less cost dollars and a very less EUI. So I'm just going to start by running a basic one, which is here. And it's running. Okay, still running. Anybody have any questions in the meantime or any suggestions? Okay, so we have our first iteration. Okay, so this is with 20% glazing, right? You're saying only with the 20% glazing, very basic features, 7-floor office building. We have an EUI of 122, carbon emissions of 99.8, and of course the cost premium is very less, like $7 is pretty good, pretty decent. So what do you guys think? That doesn't make sense? The more unsustainable the building is, the more cheaper it is, or?
We can do better.
We can do better, okay. Okay, so I think we should start with 40% because we're architects, right? We're gonna design a building with at least 40% windows. So I'm gonna keep our base building with 40% window to wall ratio and run like another, yeah, it's running again. Climate Studio actually pretty quick. Like I think it takes about 10 seconds to run this whole thing, which is pretty great. And yeah, there we have it. So our EUI is with 40% just by changing from 20% window to wall ratio, 40%. We have our premium just went up to $14. We have a EUI of 134 and carbon emissions of 110, which is what we have here. Jonathan, wait, do you want to take a screenshot of this for our presentation? Yeah, okay, you got it?
Yes, I do.
Okay.
Ashu, you already had us in a better position before. What am I talking about?
Yes, but we want bigger windows, right? We don't want tiny windows. Okay, so.
I don't know, I hear I hear that we only get little small windows for passive house, according to some.
Yeah.
I wonder whether we can.
So this. Yeah.
Oh, sorry.
Sorry, go ahead.
I wonder whether we can, tune this somehow.
With the envelope settings.
Yeah.
Or
any suggestions for shading? Like.
This is open to everyone, not just us.
Which
Yes.
way is north?
Yeah, I just
So-
typed on the chat about improving the roof design to start with. I don't know if
Okay.
everyone.
That sounds good.
All right. Yeah, we could start with roof design. So we have currently the roof design of 14.1. Should I make it 18?
Oh, go all the way
or
up.
28. Go all, okay, 56. Okay. All right. I mean, we are talking about New York here, guys. So let's see. So
I think we might be
had,
surprised how it
EU
impacts.
Yeah. So we have an EUI of 134. Let's see what that changes to.
There's only one roof and it's a 7-story building.
Yeah, so I would say surface area is sort of working towards other areas, maybe having a greater impact. Is that the results?
Yeah, that's the results. And it didn't impact it much. It was only 1 EUI less.
Wow.
So
1 point.
So one of the things
Yeah.
that Kim Shen said to us in the presentation he did back in July last year is you can do these sort of quick envelope calculations where you sort of look at your weighted averages of, vertical facade versus roof to begin to get a sense of where you're going to get the biggest bang for your buck. And it doesn't even have to require an energy model, just to sort of know, like, I've got 80% of my building is going to be exterior vertical facade versus say 20% roof. And
Yeah.
you sort of back into some quick calcs on things that way. Anyway.
Yeah.
So
any other suggestions for what you think would reduce EUI and carbon emissions?
facade R
We
value.
have,
Yeah, well, is there like a way that you can, so would it make sense to like to set the roof back to what it was originally and then
Yeah.
just do the insulation?
yeah, we definitely want to do that because we also have a
There's a
cost value.
cost,
So we
right,
want to keep the cost premium low. So, okay, I'll set it back to 14 because we know it's not going to make much of a difference in terms of the roof, changing the roof R value.
So does the model take into account the buildings adjacent to it, shading?
Yeah, it does.
So why don't we look at shading for the 2 exposed facades?
And someone had asked
Shading
earlier
for the
about the
two-
orientation of this. So what's north in this model?
So in this model, you're looking, this part is north and this is south.
So
we're looking at the south facade here.
we definitely want shading on the south facade.
So we want
So-
shading on the south facade.
Yeah. And do you have vertical
go for-
shading for the west, or what kind of shade?
No,
Is it only
we
horizontal
only, Yeah. In this exercise right now, we only have a horizontal shading.
Maybe
Should I do?
maybe do
Yeah,
shading
go
on the
ahead.
south and maybe reduce the glazing percentage on the west. Just for fun.
Okay.
Sounds
Okay.
good.
Do 2 feet shading on the south, and on the west, I reduce it to 20%. Okay. All right.
I thought you liked glare, John.
Should I Okay. Should I also reduce glazing on the east facade just because there's so many buildings? You're probably not going to have much bigger windows in there, right?
Yes.
Yeah, you want privacy anyways.
Yeah. Okay. So let's run it. So our previous value is 133.8. So let's see what this comes up to.
And the previous cost was 27, just for reference.
Yeah, so we're doing pretty good. We're at $11 cost premium and an EUI of 124 or so. That's a pretty good. We're starting off. We're getting on the right foot here.
What's the R value of the
yeah.
opaque part of the walls, exterior walls?
Yeah, that was someone else's suggestion before.
14, pretty low.
Should I change it to 28?
Sounds good.
Okay.
I wonder what if you take the shading off, so it's just about amount of opaque to transparent, but nothing additive.
You're saying no shading in the south facade?
Curious, yeah, perhaps.
Okay. Okay.
Anybody else think
also
that the wall's going to not do much at all? I feel like 14 for a wall, if that's true R, is pretty good. There's not that much wall here.
Yeah.
Is it just me?
Yeah.
I agree. But let's
let's
run
it. But
let's go to the tape.
That'd be my guess.
That sounds.
You got me nervous.
Okay. So should I keep it or change it?
Keep it. Keep it.
No, keep
Okay.
it.
Keep
We gotta
run it. Let's see what happens.
Okay. Got it.
Place your bets.
Yep. Yay. Someone.
Yeah. Who's the house on this?
The client is the house, I guess, right?
I'll bet the house on this one. 115.
Nope.
Oh man, I
Oh.
lost. I shouldn't bet against
Wait,
Jonathan.
how much was it before, Jonathan?
It was like 124.
Oh, I see.
Let's see. Oh, sorry. 124.1. So yeah, it did not save a huge amount.
But we did remove the south shading.
We saved. Yeah, interestingly,
we took a
cost
premium
went,
off.
The cost went up, I think.
Yeah. The cost of insulation is, I think, $5.
Gotcha.
Yeah.
I'm interested to see what changing some of the factors over, I think it was over in under systems or something. Like I noticed it said fluorescent. And if we start to update that kind of thing.
What?
Yeah, like what if we change that to LED?
Okay.
Oh, yeah, that's big
Oh,
money
if we're gonna
right
do
there.
that, should we not go back to like your original baseline? Or at least
Should
take the
we?
insulation out.
Right.
Do that much.
Yeah.
I'll take the facade off, but I think I can keep the south shading. I think that was useful.
I think we're gonna see a big impact by that.
Okay, let's see how much light it.
Can you also go to that, since we're dealing with the systems, there was one about dimming.
Mm-hmm. Yeah, I can do that. So I can select dimming.
Just as a time check, we have about 14 minutes left. Just keep on rolling. Don't worry. Just
Okay, so basically, just kept LED and dimming this time. Our cost premium is 26. Let's see what the EUI comes up to be.
What do you think, Jonathan? I think we're gonna be better.
I think it's gonna be better because the lighting is a big piece of that, of that stack.
Are we gonna see a drop by 10? Maybe.
Ooh, that'll be good.
Ooh. It's taking more time now because we have LED lights. No.
Big money.
Yeah.
There we go.
There it is.
So what was this? This was LED lighting and something and dimming, or
dimming, but we added the shading
LED
back to the south.
And dimming. Yeah.
I didn't realize we weren't on LED, but can we look at the heating system too? What are we using?
All right, hold on. Can you go back to
go
back to that view?
Yeah.
So I can capture it. Sorry, gang. This is not perfect screen capturing, but we gotta write the story. Yeah. Okay. All good.
Okay. So we have some options here for currently we have HVAC baseline. We also have a conventional heat pump and high performance heat pump.
Let's
Heat
go for the high
recovery.
performance.
Yeah, what if we go with the heat recovery?
Heat recovery. Okay, but let's just check what is the premium. We're 26. So if I change it to heat recovery, we're gonna have a premium of 41. Okay.
Can we
I'm gonna run
change,
it.
reduce the shading or something else cost?
Yeah, we can do that next.
But we haven't done
But
life
just
cycle costs.
FYI, yeah, and also the HVAC cost is more expensive. So the HVAC is $15, but your shading is just $2 per facade. So think about that.
Oops.
Yeah.
Oh, sorry. So what? I'm sorry. How do I describe this one? This is heat pump.
Well, this is LED
yeah,
plus high efficiency heat pump with heat recovery.
Heat recovery.
Yeah.
It's
Exactly.
What about the U value of the windows?
There we
Yeah.
go.
We can change that too. So what is the premium
sorry.
again? 41.
Sorry. Yeah. Before
Oh,
you
sorry.
before you
You
go,
gotta get your screen capture.
Okay.
I'm
Yeah.
not. I'm slowing you all down. I realize that.
No problem.
I'm typing notes instead of. Okay. Here we go. All right. You're good.
Okay.
the cost down. Make the windows smaller a little bit.
So cost premium is $41. If we change it to double panel LOC, I believe our cost premium became 46. I can change it to triple pane LOE. What do you guys think?
It's going to be a big cost premium.
Sure. Give it. Well.
Yeah.
We got to test. We got to test it.
It's good for acoustics in the city. You'll be able to charge more for rent.
You might be able to get rid of perimeter radiation.
Oh, we have perimeter radiation?
No.
We don't know.
We don't know. But if we got triple
That's
pane,
not even one of the choices.
A nice quiet building.
Yeah, right.
Oh, it went up.
The triple pane.
Yeah.
internal heat loads.
We're heating load dominated. That's why.
Let's go back to the middle choice on the windows.
The double low E.
Yeah.
Okay. Let's see.
So the south looks like that's the 40% glazing, and the
yeah, east-west is 20.
And then the north is,
I think that's 40 as well.
40.
Yeah.
What if we switch the north to 20 or 30 and increase the west? Well, it looks like we're shaded by those other buildings.
All right. So what is this? Sorry.
Low E.
There we go.
Double pane.
That's better.
Yeah. See.
Yeah.
How is this? So how is this different than two iterations ago?
Yeah. What was the cost premium in this one?
Default glass is no low E, I think.
Oh, this is just
correct.
But what was the cost premium? Because the EUI is only marginally lower than what it was before. So I was just curious what the cost premium is for the low E.
Let me see.
To double pane clear, to the standard double pane, not to the triple pane.
Yeah, so double pane was 41. Double pane low E was 46, and triple pane is 50. So
yeah, I guess my only point was the EUI, the reduction in EUI with the cost premium from the baseline. I just don't know if it would get us a whole lot. if we're
Yeah.
trying, you know, if we're also trying to balance the cost premium.
Yeah. And if you see here, yeah, the EUI in the last 3 iterations was almost the same with like 1 or 2 with like very less difference. So I might just go with the basic one, double pane.
What's
clear?
What's represented by that gray box in the graph?
With that
That's
would
our
be
biggest
equipment.
chunk that's left.
Yeah.
And how do we mess around with that?
That's probably plug. I
So-
bet like plug loads and
Yeah.
stuff, maybe.
Yeah. So because this is equipment and it's a typical office building, we're not gonna mess with plug loads for now.
Oh, okay.
But that's the right move, right? Isn't the next move is
Yeah, go after the big boxes.
yeah, get rid of
Yeah.
you know, all of the computers, de-densify.
Yeah.
Can
Make
you
sure they're
pan
all
over?
laptops.
Can you
no
pan
heat
over
load
to
right
the
now.
other controls there? Yeah.
Yeah, so I can do that. So if we see here, in terms of EUI, most of our energy is coming from equipment. We have some from fans in the summer months, light throughout the year, very less hot water, which is good, and very less heat in the winter. But I think most of our energy is taking up because of the cooling.
Could we
From cooling.
increase the shading
Yeah, we can do that.
since that was like cheap, and if we just increased it like
Yeah,
to
want to
4
shade the
foot?
west now?
Yeah.
So west? Should I go for 2 feet or 1 feet?
Could you do like 2 feet on there and then
2 feet on east and west.
East and west?
Yeah.
Okay.
I don't know if east makes a lot of sense though, because it's
Wait,
right up
east?
against the other building.
Oh, yeah.
Yeah, you meant south.
Well, we already had south.
But
And
maybe
in
go,
the, and
would
in
it
the
make a
early
difference
mo-
to increase south
Increase
that-
south.
deeper depth?
to 4. I agree with
Increase-
that. Let's try it. South to 4,
4?
maybe?
So there's
3.
Three is
three.
most.
Our
Three's-
maximum is 3.
Okay, that's good.
Zoning limits you to 3 foot.
Yeah. Pigeons go
Okay.
for 4 feet more than the 3 feet. Yeah.
Then you get a constant source of eggs.
Right, exactly. Or something.
You'd have to make the windows operable though.
Yeah. It didn't make much difference. We're in the same range. I think it was 68 before or 67,
Yeah,
and we're
I
just
think that's right.
yeah. So
I think it was less than
changing
that. I think
the-
it was only.
Yeah.
I think it was only like 0.4 of a change.
69.5 was the double low E, and now it's 69.6.
oh wow.
But it saved $6
Okay.
because it was
Okay.
$50 premium for the double low E.
And what if we look at that other chart for July, which was our high cost month?
This chart?
Yeah.
Mm-hmm.
So the cooling cost doesn't look like it went down very much.
Yeah, it didn't.
And it looks like the shades are just automatic horizontal anywhere you're placing them, as opposed to having vertical on those westerly facing.
Yeah.
Yeah. Yeah.
If you scroll down
Fans.
on the screen, I think the other graph shows a balance. If you look, so this one does break up into like an energy balance of the different, what's causing the
Yeah.
the
So of course,
load.
equipment is a major load.
Right.
We have some heating, people, windows, and E and D.
I don't know what
mechanical
EMP is.
vent system.
But I think
we have one more setting that we haven't tried,
Oh, yeah.
which would be the operable windows. We could try that in our last remaining 2 minutes.
Oh yeah, look at that.
Uh,
Time. Wow.
Oh yeah.
There's a premium.
Yeah.
Run it quick.
Yes, that's
Yeah,
gonna be
but that would
premium, I'm sure.
actually work for the spring and fall.
Yeah.
Any last suggestions for, okay. Any more
I think
changes?
let's run that. Yeah, let's
I
run
like
that.
that.
It's the only one we didn't try.
Okay, okay.
Who doesn't like operable windows?
Almost there. With 1 minute to go. Yeah,
A little bit.
a little bit. It went from 69 to 66. So that's good.
All right, sorry, let me
Our
get
problem
this.
is, our biggest problem is still that cooling load in the summer, right?
Yeah.
Yeah.
So really, if we wanted
Wait,
to fix this, we would make our south window smaller. That would help
Yes.
our EOI and our cost.
Mm.
Or we should do what the Italians do
occupancy
and
down.
spend July at the beach.
Yeah.
I like that.
Schedule, yeah.
Jonathan, you got the screenshot?
I got the
Is there
screenshot of that.
an Ibiza toggle?
Do you want to zoom
Okay,
in on
I'm
the,
running.
Yeah, I'm sorry, running one more. And then we're all going to
we
go
have
back
15
automatically,
seconds.
so thank you.
Yeah.
In 10 seconds.
You may need to screen capture that one yourself, Aishu.
Okay, I'll do that.
Great. Thanks, everyone.
hope-
Thank you.
Oh, we got, looks like, oh, we have a respite, 56 seconds. it
Oh.
said. Excellent.
Oh,
There's
let's see if
setup. See if we get one more.
if you get a better EUI.
Should we try the south window? Making it smaller?
Yeah, that's what I just did. I
Oh, you
just made the
did?
south window
Oh, okay.
smaller. Yeah, I made it the 20% opening. Oh, come on. So close.
No matter how fast it is, we're quickly impatient. Yeah.
Oh,
It went up. It was 66.1. It went to 66.5.
Yeah.
How much money did we save for that?
Hardly
$2.
We lost $2.
And a lot of
We
quality.
saved
of
$2 and
space.
we lost
30 minutes to optimize a building? Never.
Piece of cake.
Never enough.
Yeah.
we ran out of time.
That's what the consultants charge for. Being a consultant, I'll say that. But hopefully you guys had a preview of how and what it looks like. And we had some discussion around the results and the iterations. The idea is that Climate Studio, Ladybug, Honeybee, Cove Tool, all these tools are available for early design simulations to use as a comparative analysis. Not the EUI number doesn't matter, but what matters, how do you get to a lower, and how can you reduce the energy use? So it's totally possible to take Climate Studio, for example, to take Ladybug, Honeybee, and create a similar dashboard for your company, for your project, with very specific templates to say, the most common glass products that you use, maybe, or the building types that you work on, and things like those. And for each project, you could start with that, having a discussion with the design team, going through multiple iterations, understanding what factors really impact, what does not impact, and then that can help in having a more intelligent discussion with the consultants as well, and setting a target. Really, I think that's more important to understand where you want to be and how you can chart a path to how you can get to that target.
Thanks, Apoorv.
Mm-hmm.
So I had some takeaway questions. We have some time to have a discussion. Oh, I wish the breakout session was a little longer. But what strategies or upgrades worked the best in reducing your EUI? What was least effective? And maybe, do you trust your results as far as a comparative analysis is concerned? Would you feel comfortable using this in your office? And not limiting it to the tool itself, but and then, how will what you have learned during the simulation game impact your practice? It's the little typo there, sorry. We can open it up to questions and comments. Do any of the team leads want to kind of share what their groups tested? I guess.
Yeah,
I can start. I mean, we were able to just.
I could share, Apoorv, I could share our screenshots and you could
go ahead.
Talk to this. It says
I
cannot share.
I mean, we were able to just share or test some fenestration values and look into some of the envelope performance as well. So one thing we realized was we started off with a non-code compliant building with our 14 walls, for example, which will hardly meet probably any code at this point of time.
Right. So are folks seeing my screen here?
Yeah.
Okay. So,
but we're seeing the main presentation. Yeah, that one's
okay. But wait, I had the other one. Did that get saved? Oh,
it's right there. You just
here. I have it.
Okay. Sorry about that.
Oh, you got it.
Yeah. Okay. Here we go. I guess I closed it inadvertently.
Skip over ours. We had a model problem.
Technical difficulties.
Here we go.
Oh, really?
All right. I think I'm getting there. Pardon me. All right, I think we were group 2, right?
Mm-hmm.
All right, it's there.
There you go.
Hadn't had a chance to format it very well, but I guess Apoorv, this was our kind of out of the box.
So the first bar really was the one that we started with 20% window to wall ratio. The next bar is just increasing our north glazing to 80%. Mm-hmm. And our energy use increased a little bit.
I made a note that we went from $7 to $10 for that.
Yeah, I think till the time we on all our simulations, I think we were just adding cost. Mm-hmm. So we were just coming to the VE part of it before we, as good designers, we just stopped there.
This is really a demonstration of what not to do. I think so. Here we upped our south glazing to 40%, but we did add a 1 foot overhang. So we actually changed 2 variables here, and we saw a $12 cost, a relative EUI of 128, and we were at 127 before. So the additional glazing didn't hurt us too much there, I guess is the best we can say. So here we started to really, I think, mix it up a little bit. More expensive, higher EUI, but more glazing. So I mean, maybe what you would expect. Well, actually, so we brought the north down. We added it to the west here. That's what we did. And I guess the south overhang was 40. And I know we're if we want to let others scroll through this too. So then we moved on to from just changing the window to wall area ratios. We started looking at the opaque walls. So we added insulation to the walls and roofs, or to the walls and roof, and then really the only difference between our last two simulations was we changed from double pane low E to triple pane. I think that was our last. So notice we've kind of creeped up to $28. I think we started out at $7, right? So and our EUI has held. So we've done a good job of mitigating all of the ads, but the cost is there. So then if you go, when we went to triple pane, we were up at 34, but we actually started to knock down the EUI. I think we were at 132 before. So the triple glazing really was beneficial in New York for this glazing configuration, north, south, east, west. So
we'll get another group maybe.
Should I scroll to another group? This is Karen and Bunny.
Yeah, we can talk through this. So we did a bunch of iterations. We did a little bit less optimization and rather kind of seeing how changing things kind of worked and what it did to the overall. So what you're seeing here is our first run, which included, what was it, 20? This was just looking at window to wall ratio. I think we had 40 on our north. Oh wait, no, it was wrong.
I think it was 40 on the northeast and south, right?
Northwest and south, yeah, which, yep. And then on the next iteration, we actually reduced the west side to 20% window to wall ratio to see kind of how that impacted it. So obviously the cost reduced and we actually saw a little bit less EUI. And then the next round, we start to look at the impact of the shading on it, especially kind of in the areas in which we had more glazing. So in particular on the west and the south side, we kind of identified those as the best kind of view and or light, which is kind of why you're seeing that. And then we moved on and we kind of added east shading to see the benefit of that. So we saw a slight reduction kind of in the EUI there. Obviously the price is continuing to climb.
Right.
And I think we then increased the shading, I believe, on the south side and took away the east shading. We decided it wasn't worth that cost on iteration 5. Keep it on going. We started to get into the facade options. Yeah, we got like 12 runs in. On the next one, we start getting to the facade. So we started with the windows as well with the insulation kind of values. So we're seeing a 5% drop from like 127 to 119 there in the EUI and a little bit in the carbon emissions as well. And the next round we did that again, but we actually added in the roof with the highest kind of R value, and you're seeing our cost premium kind of start to skyrocket through these, as well as dynamic shading kind of as we started to combine our runs here to get them to go a little bit faster. And then this was probably like our biggest difference. We'll see kind of in the summary slide was actually putting in the LED lights along with the dimmable option. That made a big impact. Here you're seeing our EUI drop like about 20 kilowatt hours from the one before. And then we got into a heat pump with recovery.
Nice.
And did natural ventilation at the end just to see how it went. And so that kind of, we add in the operable windows, and that kind of leads us to our 2 summary slides. It actually enlarged the second one so we could see the impact of it. And we did have one iteration in there, which is number 12, which did not run fully, which is why there's no equipment in it. So that one's an anomaly. So ignore that. But
it's a lot of operational savings, even though you're adding to the cost.
Yeah, we ended with $91, so we're definitely up there. But you can see the difference it makes.
Yeah.
And that was actually
LED.
Sorry, I didn't mean to interrupt you.
Ahead,
that was a question that was raised in our group about the way the simulations run and the cost estimation. If it's assuming any savings from reductions in your mechanical systems.
No, the cost is just for the construction cost, equipment cost, not operational cost. So, it's the idea is basically to stay as low as on the cost and get as low as possible on the energy use.
Yeah, the question was more in regards to downsizing equipment as we eliminate the heating load, for example, and eliminate heating equipment now, if that is considered.
No, not really. No. Yeah, so we're not translating the savings and energy back to the cost. It's just cost of adding things into the building, essentially.
Yeah, when we did triple pane, we didn't see our perimeter radiation deduction happening.
Never did that again. Well, that was
run
a lot of
IES off
information.
for that.
But yeah, I think that's a good question.
I think this is important to understand. If you use such a model to make significant design choices, you need to have the full picture. And if certain design choices get eliminated because the cost model that you're using here is not accurate, it really hurts. And I've seen projects where these decisions were made on incorrect or incomplete cost assumptions. And we need to avoid that in our industry.
No, absolutely. And the idea absolutely is not for the designers to take this and think of it as an energy model and take decisions, but it's comparative analysis. I think the more important part is this is an academic exercise, right? It's meant to just give a picture of what does it mean that you add shading, and otherwise I can go in and say, hey, I want 80% window to wall ratios, I want shading, I want heat pumps, I want every single thing, and see my EUI is down to 20. But that's also not the true cost, right? Or true story. I completely agree with your point that there's operational savings and there's equipment saving and everything. The idea is basically to stay on the design side and do a comparative analysis and have a conversation with the consultant, with the energy modelers to understand what it means.
I would add, Apoorv, I think one way you could keep that, you could isolate that out of the discussion and really kind of make a decision not to manipulate your mechanical systems, but work on all of the envelope strategies. And then when you're ready to start talking systems, I mean, yes, you could compare, I guess, types of systems, but I think that when you start getting into sizing of systems, that is a more complex evaluation. That makes sense.
Yeah, Josh, I think that's the power of a tool like this, at least academically, is that you can, in sort of like the garbage in, garbage out that Janki had in the presentation, if you just sort of like keep your systems static, you can then just look at, how the impact of just rudimentary changes to amount of glazing, R values of wall, even, massing of building, how those things could potentially, move the needle before you then begin to talk about like, okay, what are we going to do on the system side? Because we give you all the LED and the mechanical savings, and you're gonna be like, great, I can have all the glass I want, right, Josh?
Yeah.
So we discussed that in our breakout group as well, was the thought that like you may not see, like when you're doing a comparative analysis, you may not see a huge trade-off in your whole building energy, like your EUI, because you're keeping everything else agnostic, right? You've set everything else to be just like default, and you're not concerned with everything. And so it's important to understand what is the question that you're asking, right? So if you are increasing the window to wall ratio of your south facade, when does that design change when does it make a difference in your overall building energy model? And how can you then do another series of energy models that consider the time frame that change is important? So you're concerned about your cooling loads in the summer with having that much sun, that much glazing on the south end, and you're also concerned with your heating loads and trying to understand how much free heating are you getting in the winter, and how can you compare that to your air conditioning load in the summer, given that ratio of glazing on your south facade. And you can use your monthly energy use charts with the end uses on there to kind of compare those two, right? When you do a comparative analysis. So you're not necessarily looking at your whole building EUI, because it might stay at 131 or 132 when you make a change from 30 to 60%, I mean, 20 to 40%. But it might have a huge impact on the other things that are more granular and specific to time, like time of year.
Is it possible to share those, the monthly and those energy balance diagrams, and talk a little bit about those? Because we found in our group that was kind of useful. We ran some different iterations, and then people started chiming saying, oh, this is where the energy is, let's look at lighting, or let's look at this. Because I think, beyond the results, I think like just the process of talking through it and as a group saying, what should we look at next, is like, maybe that's the, that's a great takeaway too.
I believe in the next session, we're going to do a bunch of examples where we talk about the process, because they're in the Architect's Building Performance Guide. There are examples, but it's kind of like a snapshot. Here's what the end results were, and this is what we compared. But we're going to kind of walk through, here's the question that we were trying to answer. This is how we set up the model. These are the tools that we used, right? We're going to walk through the different tools that that are available to us, and how the different tools were used differently to answer the same question, and then looking at the results and how they informed the next step. So that's going to be kind of like unpacking that garbage in, garbage out, and looking at the energy balance chart and the monthly energy end use chart that you see, and really diving into the details of that.
And I think, Janki, you touched on a very important point, is it's learning to ask the right questions when looking at these tools. So what variable, when you isolate, what's going to be the impact of 60% south glazing with or without sunshades? Those types of things you can legitimately compare. It gets the load calculation. That's when you start to bring in an engineer, because then you're starting to talk about what the use of your building is, what the internal loads are. And so I think I think the mechanical piece of it has to be kept at arm's length, or kind of just kept. The expectations have to be managed for that. So, whoops, I think we just lost your screen. Okay. So I think I just want to emphasize that with these early tools, the idea is for the, as we were talking about in the early part of the talk, for architects to be able to kind of troubleshoot some of these early decisions, and then by schematic design you want to be talking closely with an engineer about systems and loads, and then you start to manage those and come up with techniques to manage those.
We have a couple of ending slides, and for some reason my computer is on the fritz here.
You can pull them up.
Thanks, Bunny. I think they're your closing slides anyway.
So we just wanted to point people to the Vimeo site. We'll post this session there too, and some of the previous sessions that are related to this topic from last summer. Demystifying Energy Modeling, which was a great presentation by Kim Shin, the session on environmental design tools, and then the case studies on, the strategies for high performing projects. And so those are great resources that complement this session. That are still available on demand. We will publish and share the poster. We went over that at the beginning, but we have a lot of exciting sessions coming up. And I also wanted to connect people to a session that's being hosted on Thursday by AIA Austin Coat from 12 to 1 p.m. Central Time. And it's going to focus on sustainability action plans and goal setting for 2030 signatories. There's a link here that'll be shared out in the PDF too. And as a reminder, we hope everyone will consider joining the 2030 commitment if you haven't already. There are a lot of opportunities, including being a climate leader, mastering your data, and understanding where your projects stand and how to evaluate them, and understanding which parts of your project are performing the best, attracting clients and retaining talent, and also getting recognized for those contributions. All of the past COAT award winners have been 2030 signatories, and it's a really good practice for firms. It's really easy to do. There's a stock commitment letter that you sign and upload to the DDX, create a sustainability plan within the first 6 months, and then you begin reporting your projects within the first full year of being a signatory, and then endeavoring to meet the 2030 targets and biannual updates of the sustainability action plan. And just as a reminder, our monthly meetings are on Thursday. We hope you can join us. They're from 8 to 9 a.m. The next one's on February 18th. And we're going to have a guest presentation from the Philadelphia Energy Authority. They're going to be talking about some of the initiatives they're working on under Philadelphia's new climate action plan and commitment to being net zero. And we'll also hear from all of our subcommittees with monthly updates. 2030 commitment meets on Mondays, policy and advocacy on Tuesdays, environmental justice on Wednesdays, zero waste on Fridays, and the design awards sort of as needed. There are tons of opportunities to get involved with AIA Philly COAT. So if you're interested, please reach out to David or myself at aiaphillycoat@gmail.com. And thank you all for joining tonight. If you have any questions, I'll hang out on the line too. Thanks so much. And many thanks to our presenters tonight. It was awesome to run through those simulations and see this in real time, and to get all of the updates on the new standards that are being put forth. Thank you.
Yeah, thank you to AIA New York COAT, Apoorv and his team for joining us in this next series of sessions for our new co-chairs, Janki and Josh. Amazing evening. Thanks again for all the hard work that went into pulling this off
thanks
tonight.
for joining, everyone.
Take care. Everyone be well.
Thank you all.